Okay, recording in progress. Please go ahead, Professor Lin. Very welcome for your talk. So I think we are AIAA Air Transportation System TC, or Air Transportation System Technical Committee. So usually we meet every year in June at a conference called AIAA Aviation Forum. So it's a research conference. At the same time, our TC colleagues will also meet every year in June. So if opportunities allow, maybe in future you can join us in one of the conference so we can meet in person. But very glad you agreed to give us this talk today. So we are very interested to learn more about your work in machine learning, AI, and natural language processing in the application of air traffic control. Yeah, please go ahead. You can start.
Hello everyone, I'm Yining from Sichuan University, China. Thanks for the invitation from AIA and Professor Wei Peng. I'm very happy to present our work here for you. My presentation related to the AI-based air-ground speech understanding and safety enhancement. Here is my personal information. Please visit my homepage to see my works or contact me for further cooperation. Firstly, I will introduce our research group for you. Our group called ATS-TC, that is to say the Wise Air Traffic Control related research. Some national laboratories serve as the supportive institutions. Here are the laboratory environment, including our office and equipment. Here is the preliminary of the ATC-related work. ATC is a human-in-the-loop procedures. The ATC operation is to ensure a safety, order, and efficient air traffic operation. The aircrew performs aircraft under the ATC's guidance. In this page, the next figure shows the information flow about ATC work. ATC safety is highly dependent on the ATCO. The speech is the primary means of the air-ground communication impacted by various factors, such as the radio transmission, equipment noise, limited by psychologists and physiologists conditions. The instructions issued by ATCO may cause potential risks, unconsciously or even intentionally accidents. During this page, in aviation history, many incidents are caused by speech-based AGC, with some typical issues, such as the communication speech accidents. As shown in the right figure, over 40% incidents related to the speech AGC. The speech-based AGC procedure is required to the properly monitored to detect negotiation misunderstanding. The intent should be considered to improve the predictability of the flight trajectories and monitor flight conformance between the expected instruct trajectories and real-time trajectories. To manage the human factors in the ATC work, we need to understand the AGC speech. Here is a two-step works. Firstly, the speech recognition technique is applied to convert the speech into the text. Since the computer systems cannot process the text directly, we also need to the natural language processing techniques converts the text into ATC-related elements. In our work, we define three kinds of ATC elements, including the speech zone, controller, or aircrew, the controlling intent such as the climb, descent, and some key entities such as the waypoint name, altitude. Thanks to the available data storage, all the steps in this work are implemented by AI techniques. This is called the AI-based ATC understanding. In 2020, the CAAC has published official files to encourage the ASR application in the ATC dome to enhance the air traffic safety. To achieve the ATC understanding, in this page, I will show the research schemes including the problem and the concepts, the system design, and the solutions. By analyzing the ATC works, the key ATC procedures are suggested to be monitored to manage the human factors in the design phase. Starting from the ATC speech, we clarify the technical difficulties in the ATC work and propose the corresponding ATC AI techniques. In the solution phase, we collect real-world data to construct and train AI models. Our required information processing models are also implemented to achieve the final safety monitoring tasks. Finally, a software prototype is developed to validate the proposed approach. The machine works and the results has been published on the CGA journal. Completed the ATC understanding and safety enhancement, we need to learn the key ATC procedures. In this page, based on the real incidents, we analyzed the cause of the speech ATC procedure, which also enlightens the solutions of the ATC monitor. As shown in the table, we mentioned the non-standard terms, communication issues, readback errors, incorrect aircraft response, incorrect aircraft operations, and the potential risk instructions. This work has been published in AIAA TITS journal.
Professor Lin, this is Peng. A quick question.
I'll show the procedures of the AI safe solution, the information flow for them. The speech is firstly.
Hi, Professor Wei.
Yeah. Hey, Professor. A quick question on the previous page. I think maybe you prepared this maybe without expecting we interrupt you. But if that's the case, I can save my question to the end. Yeah, so maybe you can go through your whole presentation. I'll save my question to the end. I think you prepared this without expecting me like interrupting. Okay, I'll remember my question. I'll ask the question at the end. Sorry.
Okay.
Yeah, sorry.
Let's go on.
Yeah.
In this page, I'll show the procedures of the AI safe solution, the information flow for them. The speech is firstly converted into text by deep learning, acoustic models, n-gram language models, and ATC contexts. Using the NLP techniques, the ATC elements are extracted from the text, as you can see in the figure, the AICD intent, parameters, and the unit. Finally, the results of the ATC understanding are applied to supported the AI safety applications, such as the NIC, CIB, ARS, and PCD. Using a many data production, this procedure can be iteratively optimized to improve the system applicability. Based on the AI techniques and the mentioned procedures of the ATC work, we presented an ATC safety monitoring framework considering the ATC speech called AI Safe, as shown in this figure. Here is the system architecture to implement the AI solution, which clarifies the system interface, the techniques, and the application. The whole architecture, including the offline training phase and the online application phases, as shown in this page. After finishing the framework design and the solutions, the system architecture, I will introduce the AI-based techniques from this page, including the ASR and NLP techniques. Firstly, we review the ATC speech-related characters. We have published a paper on AIAA TNLS related to this topic. As to the communication issues, speech-based ATC is voluntary background noise and inferior intelligibility. Transmission from the radio telephone in an analog manner. Due to the limited resources, multi-persons, including the aircrew and the ATC, were published their instructions in a single radio frequency. The transmission of the ATC speech may be impacted by various factors, including the weather, the equipment noise. In current recorded system, the ATC speech is limited sample rate to save the disk space without any processing techniques. In the first page, we clarify the input of the ASR model, the speech characteristics, including the low sample rate, the background noise and the device noise, the radio transmission and the speech echoes. As can be seen from the figure, the speech features from different ATC centers are extremely different. Even for a single channel, the speech features are also impacted by real-time factors. In this page, we reviewed the output of the ASR module, the vocabulary, including the following difficulties. Firstly, in China, the ATC instruction is multilingual speech. For domestic flights, it's in Chinese, and for international flights in English. The ATC terms are all in English. That is to say, the multilingual speech in a single entrance is usually exist in Chinese ATC instructions. For the ATC air traffic related terms, the code switching, the general ATC terms, including the airlines, the location-based, such as the waypoint names, and the phase-based terms, such as the runway only for the tower phase. The right table provided some ATC instructions and a special vocabulary in the ATC work. For the ASR research in the ATC work, another issue is the unstable speech rate. In general, the ATC speech rate is higher than that in daily life. In addition, the native speakers, the Chinese, speak Chinese speeches is higher in English speech. Meanwhile, the higher workloads induced the higher speech rate for emergency or emotions. The table provides a comparison of the speech rate between the ATC speech corps and the common ASR speech corps, as well as their standard deviations shown in this page. The next issue is the imbalanced vocabulary in the ATC speech corps. The imbalance includes the Chinese and English speeches, and some widely used words such as airlines or the digits, or some outer vocabulary words such as emergency terms. As shown in the figure, for both the Chinese and English speeches, about over 40% of the vocabulary words are only in less than 10 times. Shows a long-term problems in the machine learning research. Finally, to achieve the AI-based speech understanding, the speech corpus is also a major issue in the ASR research in the ATC work. As we know, the ATC, the speech dataset is essential of the data-driven methods in the AI research. Concerning the following issues, in the ATC DOM, the data collection concerns the ATC safety and distributed in different locations. The annotation is highly expert dependent and costly and laborious. In summary, the ATC speech is in multilingual and pronunciation scales and small simple problems. From this page, we present the topics about ASR research in the ATC work, including the end-to-end models, the multilingual speech recognition, the small samples, the feature representation, the runway-based model, and the feature fusion. Here we list our published papers and patents in this page, including some top computer science related journals and the Interspeech Conference. This page we present the topics about the NLP research in the ATC work, including the spoken language understanding, the text generation, the role identification, and the sentence segmentation. In the right of this page, we list our published paper and the patents, including some top journals such as the AIAA, TITS, and the CGL journal. Some research topics, research works about the human-machine interaction are also printed in this page, including the air-cooled readback generation, the TTS, the high-efficient deep learning models. Here we listed our published papers and software copyright in Chinese. This page, I will show some key research papers about our research. The references are also provided in this page. If you are interested in our work, please set them in your future works. The first paper is an unified multilingual ASR frameworks in the ATS work using deep learning works. This paper has been published on AIAA NNLS journal. The architecture is shown in the figure. This framework is cascaded by the acoustic models, pronunciation models, and language models, converting the speech into the multilingual forms and further to the text. In this framework, a multi-scale CNN model is proposed to calculate the volatile background noise and the unstable speech rate. Finally, the proposed approach is validated on both the ATS speech corpus and the common ASR corpus. In this page, we reported a paper about an end-to-end multilingual ASR framework based on neural networks, published on Applied Software Computing Journal. The architecture is shown in the figure. The presentation learning is proposed to learn high-level features from unlabeled speech, which helps to reduce the requirement of the speech corpus. The feature reconstruction-based pre-training strategy is also proposed to initialize the trainable parameters to enhance model training. Finally, the proposed approach is validated on both ASR corpus and the common ASR speech corpus and ATS speech corpus. Page, we reported a paper about the transfer learning techniques, which is applied to enhance the performance for different ATS centers. This paper has been published on neural computing. The architecture and the training strategies is shown in the figures. A two-stage training procedure is proposed to enhance the model performance, which also reduces the requirement of the speech corpus numbers. This page, we reported a new work published on IET-ITS journal to unify the pronunciation scales of the Chinese and English speeches. A pronunciation-oriented vocabulary is designed by splitting the English words into subwords. The hybrid feature embedding and residual conditions are also applied to enhance the final performance, as shown in the figure. In this page, the context-aware language model is designed to improve the applicability of the ASR model in real-time ATS environment. This paper has been published on Aerospace Journal. The SID from the ADSB information are regarded as the prior knowledge to enhance the cosine recognition. The synchronous-to-synchronous architecture is applied to fuse the proper knowledge and the speech features to generate the final output text. Finally, we reported the ATS speech corpus paper. In this paper, we introduced a real-world ATS speech corpus. This paper has been published on InterSpeech 2020. The speech corpus is collected from real-time ATS environment with both the Chinese and English speeches. More details can be found in our paper. In this paper, some baseline models, including the Deep Speech 2, the Jasper, the Wave2 Nature++, are also tested to provide benchmark results in future research. In this page, we present a review paper about the ATS understanding, including the ASR, NLP, and speech recognition techniques. The technical difficulties are analyzed to enlighten the possible research topics in the ATS work. This paper also concerns the potential applications of the ATS understanding. Finally, some research topics are provided to assist the future research. On this page, I will introduce some papers about the human-machine interactions based on the speech recognition, natural language processing, and TTS techniques. This paper has been published in AIAA THMS. All models in this framework are implemented by deep learning models. This framework is able to automatically read back the ATS instructions to assist the ATCO training. Facing the COVID-19, this framework can also support the implementation of the cloud ATCO training. In this page, I will introduce a short NLP task paper. The paper is to generate the readback instructions for air crew based on the ATCO instruction, which has been published on KBS Journal. This task is defined as a text generation in the NLP work. The sequence-to-sequence architecture is improved to achieve this skill, in which the multi-learning tasks, including the SRU, the text generation, are applied to optimize the model. In addition, the COP network is also designed to output key ATS words from the input sentence, which is adaptive for the ATS work. The mentioned papers are the primary research outcomes about the AI-based techniques in this research work. Our research was supported by several NSFC channel projects and the Sichuan Science and Technology projects, as shown in this page. After completing the techniques research and the software development, in July 2020, our software prototype has been deployed in Chengdu ACC, Chengdu Aero Control Center, China. The two pictures shows the system deployment in the real ATS environment. Apart from the Chengdu Aero Control Center, China, our proposed systems are also deployment in other ATS centers, including Chengdu, Changsha, Chongqing, and Guiyang. The flat phase concerning the tower, approach, and aero control center. As shown in the pictures, they are deployment in real ATS environment. In this page, some possible topics in the future works are presented, which also can be found in our review paper on Aerospace Journal, including the speech qualities, the context, the architecture, the speaker recognition, the decision making, and other tasks. Please see my papers to check the detailed research topics.
769连续成都133.65，可以吧？
风54晚4下12保持左转向东舞动，飞航天红人
On this page, I will show some examples of our systems. The first page is the ASR technique for noisy speech. As can be seen from the results, the proposed model can also obtain the desired results in a noisy ATS environment.
Tango Cathay 289, maintain 9,800 meters.
United 61, climb and maintain 8,900 meters. 成都1号2拐4拐8，高度9008，应答区是3145。东方5辆9拐下3600保持过台本。
上8键4，四川886辆。
成都东方53拐4高度拐8，飞南冲1聊951。下边3003，自己相对小梦928。
I will show our onboard ASR techniques. On this page, I will show some real cases about readback errors in the ATS environment. This page is a readback error in aero control center caused by bad weather. Page shows cases about readback error in approach. The pilot read back the 270 or 070, and the ATCL cannot detect these potential risks. The proposed system can detect this error to assist the ATCL work. In this page, it's a readback error case in the power phase. The ATCL, the pilot, readback the hot shot or the course and further caused a conflict. The system
南方的352动物继续滑，看公司电脑。
to assist the ATCL work.
计划
Back cases are shown in this page. Some are notated in Chinese. Here is a comprehensive cases about the speech recognition applications in the enhance the air traffic safety. To save the time, I don't show the real cases. If you are interested, please contact me.
成都123点拐，南方3拐8拐。成都1号的话5319高度8100，来机拐43拐。
东方5319，你好，成都雷达已识别，上8900保持。
上8900，东方5319。
白鹭844联系成都133.65，再见。
13365，再见，白鹭844两。13365，白鹭844两。
东方945，求偏置飞卡米，下8400保持。
下8400，请要偏置飞卡米，东方945。成都南方6888，适用以后能飞附加场吗？
稍等，有相对，先沿航路。
支持现在航向飞东9洞，东方945。
对的，另外立刻停止下降，现在右转航向飞东9洞。
立刻下降，右转航向东9洞，东方945。
翔鹏9654，现在右转航向飞2拐洞。
右转航向2拐洞，翔鹏9654。成都你好，昆明83洞3，高度9500，应答机35洞正，请指挥。
My whole presentation. Thanks very much.
Thanks, Professor Lin. So you are very on time. I guess one question from me actually was answered. So my question was the language model and machine learning model you developed actually work for multiple languages, because on one slide you show some of the real accidents. I saw some of the accidents are from, or near accidents are from China, some from Romania, and I saw India. So I was going to add, yeah, this slide, and Japan, right? So actually your model can handle both Chinese and English, maybe other languages?
Currently our model only supports Chinese and English, since they are the major languages in the ATC all over the world.
I see. Yeah, my second and last question. So I know Chengdu Airport, is one of the busiest airport in the world. I think before pandemic, Chengdu is definitely the top 10, at least top 10 busiest airport in the world. So I guess the motivation or the reason you developed this model, is that because you want to use this language model to convert from voice to text, so the command can be much more accurate? Or do you want to use this model to detect some of the wrong callback? Because if I'm an ATC, I tell you to do this, and if you are a pilot, you usually will repeat my command or the advisory, like basically a callback. And then your model, is that more used on the ATC side, basically convert my voice to text, or your model will use more on pilot side, basically to detect the wrong or inaccurate callback, which has some safety concerns or safety issue.
Our model currently is mainly used in the ATC side to support the ATC work. As in this page, we also developed the ASR system on the EFB. The primary reason is the GPU computation. Since the ASR model is constructed use deep learning techniques, it requires a large amount of computational resource. In the future, we will develop some applications in the pilot side to assess the pilot works.
I see.
Yeah.
Yeah, let's see if other colleagues have any other questions.
Yeah, Peng, this is Joe. I couldn't quite in the briefing slides. I couldn't follow the accuracy results. So, if you could comment on the accuracy, error rates of the algorithms.
Yeah, that's a great point, Joe. I was before, when organizing this, I was very excited to see the AI technology and the model, and already in deployment, at least in parallel with the regular operations. The system will sit on parallel. So I was asking Professor Lin, I was like, how accurate or how confident you guys will, or the ATC will trust the system? And Professor Lin said there are some. So let me answer, and then Professor Lin, you can correct me if I remember this wrong. So he said during the real implementation, they saw some of the corner cases, like the accuracy was still not 100%, but their current major portion of work is actually to addressing those corner cases. Maybe there are certain way pilots or ATC say things that is different. So yeah, so Professor Lin, can you comment on like how accurate the model is for now, and how confident, or what's the feedback the ATC folks give it to you, to your team?
Actually, to evaluate the ASR model in our research, we have published a speech corpus named the ATS speech, published on the InterSpeech 2020. And all our paper, the results in all our paper are based on this corpus. In the corpus paper, the word error rate of the Chinese and English are the best one is here. Almost 6.3 in Chinese and 9.2 in English.
So like
actually, this paper is our the best results.
So Professor Lin, when we say 6.3, is that meaning the error, the percent, like 6% error? Like for example.
Yeah.
Okay.
Yeah.
Okay.
6%.
So this
paper.
Okay.
Has improved to about 3.35%. This is a compressive word error rate on both the Chinese and English model. It's a multilingual model.
Is there any general feedback from the frontline ATC colleagues? Like, how do they like it? How, what's their feedback? Is there, yeah.
This results also, actually, the error for the model words or the non-useless words is is not affected the understanding of the ATS speech, but the keywords such as the waypoint, the altitude, or the SID, which will limit all the following safety applications.
I see.
Of course,
so Professor Lin, I was asking, so when you guys develop this and at the ATC, either tower or center, what's their feedback? Like, do they like this, or is there any suggestion from them how to make this more useful or helpful, or in general, what's their opinion, or what's the ATC feedback?
This paper, our latest paper about the identify and management risks of the AI driving operations. In this paper, I will open this paper. We made a comprehensive investigation to understand the limitations of our system, and some suggestions from the front-end users also provided.
I see. Yeah, thank you very much.
I will share this paper.
Sure, you can send maybe the links to this paper to me, and then I can forward them to our colleagues in this.
Yeah, I will send it to the chat box.
You can send me via email. Maybe I can just forward them to later, not now, but later. Yeah.
Okay.
Yeah. Let's see if we have any other questions. If not, we can conclude today's presentation. Okay. All right, so I guess that's all from today, and Professor Lin will send his papers, maybe also, I guess, sending presentation. I guess maybe it's too large because you have a lot of video demos, voice demos, but maybe you can send us the papers, and then I'll forward this to our TC colleagues. Yeah.
Thanks very much.
Thank you very much for coming today.
Thank you. Thank you, Professor Lin.
Bye.
Thank you.
Have a good day.
Bye.
Have a good day. Bye.
Bye, everyone.